Hello everyone, I'm Yushan Du from University of Sydney. Here I'd like to introduce our recent work on the learnability of quantum neural networks. This work is completed with Minxiu Xie, Tongyang Liu, Shan Yu, and Da Cheng Tao. As we can see, the fabrication of quantum hardware has achieved big success in recent years. To date, we can use 65 qubits quantum chips, and maybe in 3 years later, we can use 1000 qubits quantum devices. In other words, we are stepping into the noisy intermediate scale quantum era, which is also called NISQ era. However, there are series of NISQ processors, which are a limited number of qubits, a shallow circuit depth, a connectivity restriction of qubits, and unavoidable system noise. To alleviate these issues, the variational quantum circuits, or equivalently quantum neural networks, have been proposed. Recent studies have employed quantum neural networks to achieve machine learning, chemistry, quantum information processing, and quantum metrology tasks. Formally, the learning tasks involving quantum neural networks can be formulated as follows. Give an input dataset Z, which contains n samples, and for the J sample, it includes a feature vector xg and a label yg. Quantum networks employ a gradient-based classical optimizer that continuously updates parameters in a trainable quantum circuit U-set to find the optimal set star that minimizes the following objective function L. Specifically, the objective function L contains two terms. The first one is the average of the loss terms, and the second one is a regularization term. And for the loss term, as we can see, Yj refers to the label of the G sample, and the head Yj refers to the prediction of the quantum neural networks. As we can see, Yj, the head of Yj equals to the trace of the multiplication of the measurement operator pi times the mixed state phi state. Despite the experimental achievements, little is known about the theory of quantum networks. The difficulties are as follows. First, the versatile structures of quantum networks. Second, the non-convex optimization landscapes. And last, the unavoidable gate noise and measurement errors. Therefore, a key issue in the theoretical study of quantum networks is what's the learnability of quantum network. Here, the learnability equals to the trainability plus the generalization. Specifically, trainability concerns whether quantum neural network can converge to the stationary point, such as global minima, local minima, or saddle point in polynomial runtime. And the generalization concerns whether quantum neural network can effectively output a sample sizes that well approximates the target concept for a certain learning problem in polynomial sample complexity. The significance to understand the learnability of quantum network as follows. As for the trainability, well understanding allows us to theoretically evaluate the performance of various quantum network-based learning algorithms. Meanwhile, a well understanding can provide guidelines to design better quantum learning protocols to avoid barren plateaus in the training process. As for the generalization, a well understanding allows us to answer whether there exists any class of concepts that can be efficiently learned by noisy quantum networks that are computationally hard for the classical learning models. Meanwhile, a well understanding facilitates us to use quantum neural network implemented on NISQ devices to accomplish certain tasks with theoretical advantages. We now move on to explore the trainability of quantum neural networks towards empirical risk minimization principle. In particular, The empirical risk minimization, which is also called ERM, is a learning paradigm that has been broadly employed to benchmark the training performance of supervised learning algorithms without prior knowledge of the data distributions. ERM measures how fast the object function used in the learning algorithm converges to the stationary point in terms of the input size and feature dimensions. Mathematically, the aim of quantum network toward ERM is finding the optimal parameter theta satisfy the following equation. As we can see, this is very similar to the problem of conventional many learning tasks of involving quantum neural networks. In this study, to ease of discussion, we consider the mean square loss, and we restrict the regulation term as a L2 norm of the trainable parameters. We remark that our analysis can be easily generalized to other loss functions. The common optimization rule to tackle ERM is the batch gradient descent method. Specifically, by dividing the training data set Z into B batches with equal size, the optimization rule at the tth iteration is formulated by this equation. As we can see, the trainable parameter theta t is updated to theta t plus 1 using this gradient. It's a sum average of the gradient of B batches times learning rate it. Specifically, the equation of the gradient of the objective function with respect to the batch BI is completed by the parameter shift rule. Analyzing the trainability or equivalently convergence performance of quantum neural network amounts to checking the following two standard utility metrics, which are broadly used in ERM. The first one, R1, evaluates how far QNN is away from the stationary point, and R2 evaluates how far QN is away from the optimal result for the objective function. The theorem 1 is our main result towards the trainability of quantum neural network under the ERM setting. As we can see, for both the utility bound R1 and R2, is upper bounded by five variables, which are the feature dimension D, the iteration T, the number of batches B, the number of measurement K, and the noise introduced in quantum system P. The result of theorem 1 provide the following implications. First, a larger amount of measurements K, a larger batch size B, a smaller depolarization error P, a smaller parameter space D, and a shallower quantum secret depth L yield better utility bounds for R1 and R2. Second, the utility bound R1 indicates that the optimization of quantum neural network can diverge for large D and P, no matter how large T or K would become. Last, the convergence towards a global minima as shown in R2 provides an insight about how to employ regularization techniques to avoid barren plateaus encountered in training QNN. Here we demonstrate that the dependence of gate and the measurement noise in R1 and R2 occurs with the empirical observations. As shown in following two figures, as we can see, no matter we use QN to tackle Hubbard model or three regular graph tasks, we can see with increasing the gate error level, the probability of success is dramatically reduced. We now move on to understand the generalization of QNN. A central tool to achieve this goal is quantum statistical query oracle. In particular, let C be a concept class and D be an unknown distribution. QSQ oracle which takes a tolerance parameter tau and an observable m and returns a member alpha satisfies the following equation. As we can see, the returned number is the statistical estimates of the quantum example phi C star. The QSQ learning algorithm adaptly fits a sequence of queries MI tau I into a QSQ oracle and exploits the response of alpha I to output a hypothesis H. The goal of the learner is to achieve this good generalization error. An illustration is shown in this figure. As we can see, the learner continuously feed queries my tau I to the QSQ oracle, and the QSQ oracle returns the statistical result alpha I, and then the learner uses the collected alpha I to infer the hypothesis H to approximate the target concept C star. We also use this lemma to understand the generalization of quantum networks. Specifically, let C be the concept class of parieties K juntas or poly-n-sense DNFs. Then there exists a poly-n query QSQ algorithm with tolerance tau that efficiently learns the concept class C under the uniform distribution. Note that all of these concepts are computation not hard for classical statistical query models. The above lemma motivates us to rethink. The QSQ oracle uses a similar behavior of the variational quantum circuit used in quantum networks, where both of them are interested in the measurement statistics of quantum examples instead of directly accessing them. Moreover, both of them are established on the noise setting. So we want to explore the connection between QSQ oracle and the variational circuits used in quantum network, and we achieve this theorem. Specifically, a QSQ learning algorithm where the distribution over the quantum example phi C star is fixed to be uniform and the observable M can be implemented by at most poly n single and two-qubit gates, can be efficiently simulated by noisy quantum networks using polynomial samples. This result implies that the following results. Recall that SQ learning algorithms have been broadly applied to support vector machines, linear and convex optimization, simulated annealing, matrix decomposition, and other tasks. Therefore, we can first examine whether the restricted QSQ learning models can tackle these tasks that outperform their classical counterparts. If the answer is positive, the result in theorem 2 implies that the noisy quantum circuit used in CN can achieve these tasks with quantum advantages. For example, since QSQ learning model can tackle parieties, juntas, and DNFs with sample complexity advantages, this implies that we can also use variational quantum circuits employed in QN to tackle these tasks with quantum advantages. Finally, we conduct some simulations to verify our theoretical results. In particular, we apply QN to accomplish handwritten digit classification tasks, and the simulation results are shown in here 3 figures, and we can see when we increase the deployation error or we increase secret depth, the performance of QN becomes worse, and this occurs with our theoretical results. Outlook. In this study, we show more measurements, lower noise, and shallower secret depths contribute to a better performance of QN, and we also show theoretical guidance to devise more advanced QN-based learning models. that are robust to investigate noise and insensitive to the barren-plateau phenomenon. Last, we show QN can efficiently learn parity, joint and DNF with quantum advantages, even with gate noise. Our future work is exploit more advanced quantum models developed in quantum learning theory to explore the potential advantages that can be achieved by noisy quantum networks. Thank you.